Hello, we're going to go through a couple of problems from 3.4 from the Willy Plus online linear algebra program. The first question we're going to do is number 5, then we'll do number 6. Number 5 asks, find the general solution to the linear system and confirm that the row vectors of the coefficient matrix are orthogonal to the solution vectors. Orthogonal is just perpendicular lines that actually touch. It can be tested, as we saw in a previous video. If you set the matrix multiplied by its transpose should equal the identity, but it also, you can solve this when it's equal to 0. So we have our matrix, and you can ignore the solution here. We take this matrix here. Oh, I forgot. You can't see my cursor as before. This is our matrix here. And we're going to set that into matrix form here. And you'll notice that each of the rows can basically cancel each other out. If we multiply this by 1/4, we multiply this by 1/4, they are equal. We can then subtract, and these end up becoming zeros. So we basically just need to look at this row here, and if we set this first position equal to t and this second position equal to s, and we'll make this first position x sub 1, we end up with x sub 1 plus s plus t equals 0. And that allows us to solve for x plus 1. It ends up being negative s minus t with x sub 2 equal to s, x sub 3 equal to t. And we'll see that these solutions are correct. Now, are they orthogonal? We can show that they are by plugging these numbers into our matrices. So we have 4 x sub 1, x sub 2, and x sub 3 equal to 0. We plug x sub 1 in for x sub 1, x sub 2, x sub 3, and we find that they are in fact equal to 0. The same goes for when we multiply it by 8, or any number. It's going to be equal to 0. We see that the definition of the theorem is if A is an m by n matrix, then the solution set of the homogeneous linear systems Ax equals 0 consists of all vectors in Rn that are orthogonal to every row of vector A. So this means that the row vectors of the coefficient matrix are orthogonal to the solution vector. Okay, so for question number 6, it's a little more complicated. We have this set of matrices here, and this set of matrices here. So it asks us, find a general solution of a homogeneous system using the parameters ST. A homogeneous system is a set of equations that are all equal to 0. So we need to solve this and determine if they are in fact equal to 0. So we can look at this system here. And if we take R1, which is row 1 minus row 2, well, it's up here, row 1 minus row 2, we can see that we end up with a row of zeros. Also, if we multiply 3 times row 1 and add that to row 3, we end up with another row of zeros. So these don't line up straight across, but once again we're going to set x2 to s and x3 to t, and we've put them in here. You'll see we have our matrices, 2 times x1 plus 1 times x2 plus a negative 1 times x3 equal to 0. If we plug in our numbers, we end up solving for x1 is equal to 1/2 of negative s plus t. That is our solution here. So then part B asks, is x1, x sub 2, equal to 0, x sub 3 equal to 7, a solution to I'm trying to go quick. I didn't want it to be as long as it was, my last one was. A solution of a non-homogeneous system. So we plug these in, we multiply our rows through our columns, and you'll see this is here, this is here, this times this is here, and we have our solution for our matrices, and we need to solve whether or not it's equal to this matrix. So we can see when we plug in our numbers, it does in fact equal -5, which is the same as saying that 2x1 plus x sub 2 plus a -1 x sub 3 plus 5 is equal to 0, which means that it is a solution to a homogeneous system, and we use the result of part A and B to find a general solution of the non-homogeneous system. X sub 1, X sub 2, X sub 3 equals 107 plus our numbers, which I put it in that way. I've multiplied the half through. So it's still, this is still a 1/2 times negative s plus t. It's just written a little bit different. So anyway, thank you, and I hope you enjoyed this.